Okay, so we'll be starting with the signals and systems today. In this particular topic, what I'll be explaining you, what are causal, non-causal, anti-causal systems and their relationship with memory, and how to and unstable systems and time invariant and time variant systems. So basically, when we go about the linearity of the system, so we'll check two properties. If we are scaling the system, like for example, if you are having an input x of t and which is giving you an output y of t, then if you just multiply it with any constant number, it can be 2, 3, 4, 5, any number, ax of t must give you same result y of t. And even after, for example, like y1 of t is equal to, let's say, a x1 of t, and y2 of t is, let's say, equal to b is any constant number x2 of t. So their addition, right, x1 of t plus x2 of t should give you y1 of t plus y2 of t. Then we say that this system is a non-linear system, sorry, a linear system. And if any of the one condition fails, then we say this is non-linear. Now, causality of a system, what it means is basically at any output time, okay, t will depend only on the present input x of t, okay. It can all or the past input cannot depend on the future input, okay. So mathematically, if you have to write a causal system, so let's say yt naught, okay, depends on xt naught, okay, yt naught xt, and the condition is this: t should be always less than or equal to t naught, right? That is, your time should be always less than or equal to t naught. If this system fails, let's suppose y of t you are having is equal to x of t. So at any present value, you are having the same value of the system, or y of t is equal to x of t minus 1. So your present input is governed by the past, so past and present are satisfied. So that means your this time, okay, this t minus 1 is always less than your actual time t, right? So this is also causal, this is also causal. But if you have a system like this, y of t is equal to x of 2t. Now you see your time t is greater than, right? Time t that you are getting here is greater than 2t, which is not satisfying this condition. Okay, it should be less than. So this, at this time, this also is covered by the, now suppose for example you put t value is equal to 1 there, right? So what would be at your input, this t value will become 2, right? So it is governed by the future input. So this system is not a causal system. This system is a non-causal system. Now output depends on the future input. Let's say here we are just adding t plus 1 x of 2t, x of e to the power t, right? So now you see here x of e to the power t. Basically, what happens here? You are writing y of t is equal to x of e to the power t, right? So if you put t is equal to 1 there, what will happen? X is governed by this function e power t, right? So e power 1 is equal to 2.70 something, okay? And e power minus 1, there's my calculator over here. So if I want to write shift e, where is that e? Okay, so this is your e power minus 1. Okay, this will give me 0.367. Okay, so e power minus 1 is giving me a value 0.367. So this signal, okay, is a non-causal signal. Non-causal, or to be precise, this is an anti-causal system. See, non-causal systems are those systems which are dependent upon past, present, as well as the future values. Like, let's say you are having a system x of t plus 1 plus x of t is equal to y of t, right? So what you are noticing here, this depends upon the present as well, right? Hmm? And as well as the future. So this system, categorically you can say this system is a non-causal. Why? Because one of the system is making it non-causal. This t plus 1 is making it non-causal. Now if you had this system y of t specifically x of t plus 1, okay, in this case this system only depends upon the future values. No matter t value you put 0, here the t value you are getting 1. So if a system only depends upon the future values, output depends only on the future values of the input, not present or past, then the system is called as anti-causal. Now notice one thing, all anti-causal systems are non-causal. Okay, so we can conclude here, All anti-causal systems are non-causals, but not vice versa. Because all non-causal, you can see all non-causal signals will not be equal to your anti-causal, but LT-causal systems are section of this. Now, example here I have given x of t plus 1, right? So this you see, this is anti-causal, but it is also, you can say this as a non-causal, right? Anti-causal is a part of, suppose in the exam, if they are specifically mentioned anti-causal, then you have to mark anti-causal. If they have given an option non-causal, then you will put non-causal. Here you see, this is not an anti-causal signal, right? Why? This is not an anti, this is a non-causal system, non-causal, right? Because this is your future and this is your present, okay? So you can say this system is your non-causal, but not non-causal, but not anti-causal, right? For anti-causal only the system has to be this. Same example I have already given you in the behind. Same thing I have written. I will write this for. So these examples I have already given you. Okay. So this mathematical definition also I mentioned. So here I have written. You can just go through this mathematical part of it. Now, what is a memory and a memoryless system? So suppose the system will be having a memory, if the output at any time t will also depend upon the input at any time other than t, that means past and the future values. Now you see here y is equal to x of t, v is equal to ir. So this is not having any memory. Just when you are switching on your bulb in the room, light suddenly it will come. Switch off the bulb, suddenly it will go, like a memoryless system. Okay, now it here you see y of t is equal to 3x of t. Again, this is like only a constant factor, but again, this is a memoryless system, right? But if you are having any system like y of t is equal to xt plus 1, so future value, t minus 1, past value. So, okay, so this is your future, depends upon future, depends upon past. So it is having a memory. Now, what is the relationship between a causal and a memory system? So a causal system depends on either present or past values, or at times also future values. Okay. Oh, no, sorry, present and past, that is for non-causal. Then a causal system has said to be having a. Now, if you look at this y of t is equal to x of t, right? It is what? It is a causal system. Why it is a causal system? Because it depends on present values. But t minus 2, right? It is depending upon the past values. So depends on the past values, and also it is having memory. So we can say that a causal system can have memory, a causal system cannot have memory. Now here you see integration here is ranging from the past values, right? Mind past to the present, okay? But in the past to the present, you are having memory. So it is having a memory. It is a causal system, okay? So suppose it was from here minus infinity to 2t, right? T value should be always equal to your tau value should be, okay? Either it should be less than or equal to t, okay? If your t goes greater than and equal to 2t, right? In this system, it would be non-causal straight away. It would be non-causal. Now here you see this is t na. If it was minus infinity to 2t, x of t dt, then it would have been a non-causal system. Okay, so this thing you keep in mind. Now, non-causal systems relationship with memory. So this is a non-causal system x of t plus 1. Okay, depends upon the feature value. T plus 1 is having memory. Okay, this is also, so all the non-causal and anti-causal systems will be having memory. Only for the case of a causal system, it can have memory, it cannot have memory. This is very important. Okay, so, and as far as the anti-causal is a system as present, the only difference in anti-causal is that it does not depend upon the previous or the past values. It is only governed by the future values. And so all anti-causal systems are having memory. Okay. Now the causal systems can be physically realizable, like electrical heater. Okay. So y of t is equal to k, yeah, your RC circuit, right? This is a causal system. Okay. Microphone, amplifier, speaker. Okay. Output sound depends on the past and the present sound. So these are non-causal systems are not physically realizable. Now here you see one of the system is given and it's asked to just check its y of t is equal to x e power t, right? Now I will tell you this system is causal or non-causal system. Now, if you carefully analyze this question, let me just see the, yeah, this is 2.34. Yeah. So yes, yeah, this is the system. Y of t is equal to x e power t. Now, if you look at here, what you have to do for linearity, so you just write y1 of t, that would be equal to a x1 of e power t, right? Y2 of t, that would be equal to b x2 of e power t. Now, if you add these, right, y1 of t plus y2 of t, that should be give you the value of this, right? That will be a x1 e power t plus b x2 e power t. So this is basically, this system is a linear system. Okay, that is confirmed because y1 of t will give you a this thing. Y2 of t is this value, which is equal to y of t. So this is 100% a physically realizable system. Now, as far as this causal and non-causal part of this system comes into picture, now here you look, this is given as y of t is equal to x e power t, right? So that means this has to be what? See, again, I told you, if you put t value here 1, okay, this e power 1 value will become equal to 2.7601. So for every t value 1, the other t value at the output is going beyond it. For t value, either it should be equal to your output or it should be less than your output. So in this case, this system is a non-causal system. So option would be B, linear and non-causal. Now suppose the example was this, y of t was equal to x of t e power t. Now here you notice this is a different system. So you have to keep in mind the parentheses in the bracket, which are very important. Now if this was the system, now here you see, I'll just rub this down and I'll explain you. Okay. Now here you see, I'll just rub this part down and I want to explain you that this is being asked for 2 marks. Okay, it's not necessary the same question repeat. Yet needs little bit application. So if you have the system y of t is equal to x of t into e power t. In this case, you notice here. So y of t naught, okay, depends upon what? Depends on x of tau with the value of this time constant less than equal to t naught. So if you are putting t value here, y of 2 is equal to x of 2, okay, then e power 2. Now this, why this is different? See, this is a constant multiplier here now. This becomes 2.701, but your input and output are same, right? So whatever value y of minus 1 becomes equals to x of minus 1. So when your input time is equal to your output time, okay? Output time, or your input time, okay, is less than your output time. So this is your input time. This t greater than equal to t naught. Okay, this let this be t input. If your t input is less than equal to t naught, then it is said to be causal. So this system is category. This system you see, this is a causal system. Okay, this is a causal system. As far as linearity is concerned, this is also a linear system. Okay. Hmm. So this thing you have to keep in mind. So this was asked in the gate. Now see here, one of the questions is given if the input x of t and output y of t of a system are related as this. So max 0 comma x2, then the system is C. Now here, notice, see x of t is given as a x power t. If you multiply with a y of t, so it would be max, okay, and 0 into a x of t. So a y of t should actually result in this a into max 0 x of t, right? A y of t actual result should be this. Okay, x of t is equal to, if you do a x of t, but what happens when you are multiplying it with this a y of t, a max 0 comma x of t, but for linearity, you see y of t, if you multiply this max 0 comma ax of t, you are getting this equation, right? When you are multiplying the input with the function a, okay, this function. But we need what? A y of t, a max 0 comma x of t. So your input multiplication and output multiplication are not satisfying. So what we suggest is these are not equal. This is a nonlinear system. And when, very important, whenever you are getting a function like this max, okay, so immediately this is a nonlinear system. So memory rule basically is that clipping, okay, diode max function, okay, or in the parenthesis x, okay, if you are having a function like this explicit c, so this is a time invariant, okay, and only your functions like this are linear time invariant system. Okay, so if you are having, so now what you have to analyze here, what about its time variance or non-variance? Now if you do a x of t, let's put a value is equal to -1 and x of t value is equal to -1. So -1 into -1 will come as +1. Okay, and y of t value happens to be max 0 comma 1. So max 0 comma 1 is 1 there, right? For the inputs that I have put this 1 and 1. Now the scale input a y of t, basically, because you, what is the value that you got over there? A value was -1 and y of t max value was 0, right? Scaled output is not equal to the scaled input, right? Scaled output, so homogeneity fails, system is non-linear. This is one technique to see, or straight away if you see the max function, you can say that this is a non-linear function. Now, as far as the time invariance is concerned, you do a corresponding shift in the input. So here t is there, x of t minus t naught should be equal to the same delay in the output. But here let's see, apply the same thing. Apply here shifted input here. So your y of t becomes max x of x t minus t naught. But if you do, this is your output becomes when you delay the input, right? Delayed input. So your delayed input should be equal to your delayed output. But delayed input is this. What about the delayed output y of t minus t naught? So when you are doing y of t minus t naught, what is happening here? Max 0 comma x of t minus t naught, right? So that means in both the cases, this system is happening there, right? Hmm? So compare the shifted input. So y1 of t is max 0 x t minus t naught, and the shifted output y of t minus t naught is also this. So this system seems time invariant, right? It is not affected by the time. So think of this system as a diode like a half wave rectifier. Let's say y of t is equal to max 0 comma x of t. That means if x of t is greater than 0, output is x of t. Like what happens in a diode? If you have a voltage greater than your reference voltage, like for a silicon diode, you have zero point 0.7 volts, right? And if your supply voltage happens to be greater than this, then your output will come, it will get forward biased. If it happens to be less than 0 or a negative value, your output will become 0. Exactly what a diode does: allow positive voltages to pass and blocks the negative voltage. Negative part becomes 0. So input diode and the output. So why is, that's the reason this max function here now, whenever they are showing, results into a clipping. Okay, so this is a diode logic also you can apply here. Okay, so suppose you gave an input -2 volt, output would be 0. If you double the input also, output is going to be 0 unless and unless the voltage would be positive. So doubling input does not have any effect on the input. Diode clips signal. Okay, now, the rules to remember here is any system that clips, limits, rectifier, or uses these functions are non-linear. Instead of checking for the homogeneity and all, just see that. So here you had this function, so this is a non-linear. So t square, okay, no e to the power t inside. The rule is same for all this. So rule, remember, if the system does not depend explicitly on the time, then it is a time invariant system. Okay. Now, the trap and the gate can be looking like this. Now, y of t is equal to tx of t. See, if you shift the input output y of t minus t naught. So here you have to shift the time. T minus t naught is equal to x of t minus t naught. But shifted input is what? If you're shifting the input, so you're shifting this function, right? T is just a variable. So t x of t minus t naught. And shifted output is t minus t naught is equal to x of t minus t naught. So linear, whether this system is linear but it is time invariant, but it is time variant system, right? So y of t is equal to t x of t. If you put this t a power x t, you will get a y1 of t same way. So this system is linear, but what it is a time variant system. It is varying with time. The other trap here is, see, x of 2t. Let's check this. So that means if you are shifting the first signal, step 0 is original output is y of t is equal to 2t. Now shift the input. So x of t minus t naught, right? System output will become y1 of t will become 2t minus t naught, right? So this is t minus t naught and that is become, now shift the input, x of t is x of t minus t naught. System output will become y1 of t x of 2t minus t naught. But now shifted output is t minus t naught. So y of t minus t naught is giving you x of 2t minus t naught. So shifted input is x of 2t minus t naught, and shift from shifted output you are getting x of t minus t naught. So that means it is not equal. So exam rule is basically if you are having any signal like x of 2t wherein your this value a is not equal to 1, okay, in that case directly you can say that the system is time invariant instead of checking the condition for variance or not. So this system is time invariant system, right? Because see here also you got the same reason, y of t minus t naught, you got x of 2t minus t naught, right? So this is time invariant system. So these things you remember. Okay, so basically t x of t is a time variant. Okay, time variant, whereas this x of at when a is not equal to 1 it is time variant, e power minus t it is time variant. Only x of t constants are time uh, invariant. Okay, now let's move to the next topic. Let's go to the gate wala part. Okay, now see here. A system with x of t and y of t is defined by the input output relationship. Now you see, it is starting from a past value minus 2t, right? But I told you if the t value happens to be, now you have to tell like what type of a system is this. Okay, the system will be, so if you put t is equal to minus 2, so y of minus 2 is resulting here as minus infinity to 4, right? Y of minus 2 is giving you a future value there, minus infinity to 4 x of t dt, correct? Just put an example over there. So if you see, this is your past value and t greater than 1 is your future value. So it is clearly a non-causal system. You can clearly say this system is basically a non-causal system. Okay, so we can say this. What about its invariance? You can just see some important conclusion is there. If upper limit is greater than t, right? For any system, it is non-causal straight away. Upper limit contains minus t, 2t, t square. Verdict, it is non-causal. Upper limit is minus infinity to t, x of tau dt. It is a causal system. If it is from t to infinity, this is the futuristic value. Again, it is non-causal. Okay. If it is minus infinity to minus t, only remember that if it is minus infinity to t, it is causal. In all other cases, it is a non-causal system. Okay. So now, as far as the time invariance is concerned, you just apply this, right? Shift the output, shift the input x of t minus t naught, write it as y1 and put the output as this y of t minus t naught as y2. If this y1 is equal to y2, then it is a time invariant. That is means shift in time is keeping the signal same. It is not causing the signal to deviate. Now in this case, if we kept the if we shifted the signal here, let's say x1 of t, x of t minus t naught, right? So y1 of t was equal to minus infinity to minus 2t x of t minus t naught, right? And if you shift the output here, y of t minus t naught minus infinity minus 2t minus t naught, right? So if you see here minus infinity minus 2t plus 2t naught x of t dt. So it is clearly a time variant system. It is changing with respect to the time. If you carefully analyze this, it is changing with. So shortcut here for the gate examination is there. If t appears anywhere except x of t, right? If it is like this t x of t, so straight away you can say that this is a time invariant. Okay. Infinite integration, if you get this signal like an infinity anywhere. So this means the system is unstable. Okay. So we can say the earlier question, na, they had asked three options were given. Okay. Whether it is time invariant, whether it is stable, whether it is causal, whether it is non-causal. So from that conclusion, you can just govern. Okay. Now, one more question is there. Question number 4. A cascade of three time invariant system is casual and unstable. From this, we conclude. See, each system in the cascade is individually casual and unstable. So, the minimum configuration, if one system is unstable, then all the systems would be unstable. For casualty, all the systems connected in cascade series have to be casual. So, each system in the cascade is individually casual and unstable. No, at least one system is unstable. Yes, if one system is unstable, all the systems will become unstable. And at least one system is casual. This looks okay. Let's see. At least one system is casual, and all, no, this is wrong. At least one system, all the systems have to be casual. The majority are unstable, and the majority, no, two, no, this is wrong. This is wrong. Now, this is also wrong. Okay. Why each system in the cascade is individually casual and individually unstable, means if the company individually, so that means at least one system is unstable to make the entire system unstable. Okay, and at least one system is that. This is a very tricky question, right? So they are telling at least, right? That means all the three are casual. Okay, all the three are casual. At least they are using English here. So the option B. You have to be careful with reading. That's why they have asked it for 2 marks. Now the system represented by the input output relation. Now come on, it's a 2 minutes question. Whether it is linear but not, see, as far as the casualty is concerned, I can directly say this is 5T over there, right? So this is not T. Okay. If this is not T, this is 5T, it is a non-causal directly. Okay. As far as the stability is concerned, minus infinity to the futuristic value. Okay, it is infinite memory. So if they had asked about the stability, I would have directly said this is unstable system. But now they are asking about the linearity as well, right? So integration is a linear function. Okay. So directly I can say that this is linear but not casual, right? So, or non-casual, linear and non-casual. The same principle I applied, right? The same shortcut trick. It was for 1 marks. Okay. Now here you see the input x of t and the output y of t of the system are related as, see, minus infinity to t. So this is good. This is the condition for casualty. We can say x of t cos 3t dt. Now the system is, now they have not asked about casualty. Had they asked about casualty, from the limits we can say this is a casual system. Now they are asking about time invariance and stability. As far as the stability is concerned, this is infinite integration. So this has to be unstable system. So any of the option is there. There is only one option, which is no. There is C and D. Okay, saying not stable and not stable. So these are ruled out. Now this is telling time invariant and this is telling not time invariant. Time invariance you can check, right? Shift the input like this x of t minus t naught. So if you're shifting here x of t minus t naught cos 3t, because you're shifting only in this tau function, right? And y of t minus t naught will result in, y of t minus t naught is resulting in this function to be changed, minus infinity t minus t naught. So this is not equal. So that means this is not time invariant, right? This is a time variant function, time variant. So this is time variant and not stable. It's again asked for 2 marks. If you just go through this, I've written the shortcuts also. If this is infinite integration, this results in infinite memory, hence unstable. Cosine term depends only on tau. Shifting input does not shift the output, so it is not time invariant. Now, another way to check this is that assume the bounded input x of t is equal to m. So you take minus infinity to take the entire function. Now, cos of 3t for this integration cannot be greater than 1, right? So if you integrate this function, so minus infinity to infinity, okay, the other function here. So if you just put this minus infinity to t and the dt becomes your t, so this will become t minus of minus infinity, which is equal to infinity. So hence it is unstable. So final non-time invariant, not stable. Exam tricks are if upper limit happens to be greater than t, like non-causal. Explicit time functions like cos, sine, and t, time variant. Infinite integration, unstable. Thank you very much. Okay, so we'll stop here. I hope this is a good lecture.